Okay, so what we're going to be looking at now is we're going to be looking at an extension of our work on inner product spaces, and we're going to be looking at orthogonal sets of vectors and then orthogonal projections. One thing to get is that when we talk about orthogonal in 2 dimensions and 3 dimensions, this essentially means perpendicular. That is that we're meeting at right angles. And you know, in n dimensions, it's pretty much what it means too. What we most specifically want to do, though, is we want to say, okay, well, what happens if, say, for example, I'm working in, say, a complex number space, or if I'm working in, say, for example, a function space, right, where we have like f of x and g of x, and we defined our inner product space a little differently. What it means for 2 vectors to be orthogonal, then, is that it means that their dot products are equal to 0. So that's our first thing. So we have v as an inner product space. So u and v are orthogonal if u, v, inner product is equal to 0. All right? Gives us exactly the same things if we were working in, say, our standard inner product space. You know, that's what's going to happen. But it allows us to actually extend to more abstract vector spaces as well. A set, v1 through vn, is called an orthogonal set if vj is equal to 0 for all I not equal to j. So essentially, I've got a set of vectors, v1 through vn, and as long as I'm not like dotting a vector with itself, right, then the product, then the inner product is going to end up equaling 0, and that means that we have an orthogonal set. So what we do is we pairwise, we evaluate this pairwise, and then that tells us that, in fact, every vector is orthogonal to each other. A vector is called unit if the norm of the vector is equal to 1. Okay, so we've got a unit vector as if the norm is equal to 1. And an orthogonal set, v1 through vn, is orthonormal if and only if each and every vector is orthogonal to every other vector. That's the vi, vj equal to the 0 vector. Or, excuse me, not equal to 0 vector, but just 0. Not the 0 vector, but 0. As long as we're not taking the inner product of something with itself. And vi, so for every vector, the magnitude is equal to 1. Or, excuse me, the norm is equal to 1 for every I. So this doesn't, there's no restrictions on this. Every single I is going to equal to 1. So what we'll want to do with that then is that we're going to want to do this process called normalization. To normalize a vector is to actually make it unit. That's what we're talking about. So if we have v is a vector in the vector space v, and we'll let u equal to 1 over the norm of v times v, then the magnitude of u is equal to 1, and we say that v has been normalized. Okay, so what we've done is we've constructed a vector that is in the same direction as v, but that is in fact of unit length. Right, or of norm 1. Okay, so it is unit norm 1, but in the same direction. So let's take a look at an example. Let's say, for example, we want to verify that this set of vectors, -2, 1, 3, 0, 0, -3, 1, -6, -2, -4, 0, 2 are orthogonal, and then we're going to use them in order to create an orthonormal set. So we're going to let v, right, equal -2, 1, 3, 0. We'll let u equal 0, -3, 1, -6, and we'll let w equal -2, -4, 0, 2. If you remember, to prove that 2 vectors are orthogonal, what we're going to do is we're going to take their dot product and set that equal to, and see if it equals 0. So we'll first do uv, so take its inner product, and let that equal then -2 times 0 plus -3 times times 1 plus 1 times -3 plus 3 times 1 plus 0 times -6. Add those all together, you end up getting 0. So good, u and v are orthogonal. Let's try u with w. So u with w is going to be -2 times -2 plus 1 times -4 plus 3 times 0 plus 0 times 2, and that again is going to equal 0. Go in and add them all up, you'll see. And then we'll do v with w, and v with w is then going to equal, this is actually v with w, so let's do u now with w. And uw is going to end up being 0 times -2 plus -3 times -4 plus 1 times 0 plus 2 times -6 and that also ends up equaling 0. Remember that since this is a valid inner product, if we switch the order, we're still going to get 0 each and every. If we switch the order of the inner product, we're going to still get 0. So in this case, what we see is the set of vectors is pairwise orthogonal. So we have the first requirement there because we've got them being pairwise orthogonal. Now what we need to do is we need to go in and we actually need to normalize them. So the vector, we'll take v first. The norm of v is going to be the square root of, and this will be -2 squared plus 1 squared plus 3 squared plus 0 squared. And so what we end up with here is that's going to be 4 plus 9 plus 1. That's going to end up being the square root of 14. The magnitude of u will equal the square root of 0 squared plus -3 squared plus 1 squared plus 36 squared, or excuse me, plus 6 squared plus -6 squared. And that'll end up equaling 9 plus 1 plus 36, so that's square root of 46. And then the magnitude of w will equal the square root of -2 squared plus -4 squared plus 0 squared plus 2 squared. So that's 4 plus 4 plus 16. That's the square root of 24. So the normalized vectors then are going to be, we'll call this, first one, we'll call it v1. v1 will equal -2 over the square root of 14, 1 over the square root of 14, 3 over the square root of 14, and 0. We'll call it u1. The vector is going to equal then 0, 0, -3 over the square root of 46, 1 over the square root of 46, -6 over the square root of 46. And then we'll call this w1, our new vector, and this will be -2 over the square root of 24. You can, of course, simplify that. -4 over the square root of 24, 0, and 2 over the square root of 24. And this is an orthonormal set. That is, every vector in this set is of magnitude 1, or excuse me, of norm 1. And in addition to that, we have the set is orthogonal. Okay? Let's take a look at another example. Let's say, for example, we want to verify that this set 1 sine x cosine x are orthogonal on C0 -pi to pi. Okay, and then we'll normalize the set. Now remember, the inner product here for this set is going to be -pi to pi of f of x g of x dx. Okay, so we're going to utilize that that inner product, and so we'll start out with finding the inner product of 1 sine x. This ends up equaling the integral from -pi to pi of just sine x dx. And so this ends up equaling negative cosine x evaluated from -pi to pi, which equals negative, and this will be cosine pi minus cosine of -pi, which just equals 0, because both of these are zeros. Oh, excuse me, that's incorrect. That's not right. They're both -1. So this ends up being -1 minus a -1. And so that ends up equaling 0. They're not zeros. That's right. Now, what about if we take 1 comma cosine x? 1 comma cosine x is going to be the integral from -pi to pi of cosine x dx. And that equals sine x evaluated from -pi to pi. And that, in fact, is going to end up being 0 minus 0, which just equals 0. And then finally, we'll look at sine x, cosine x. So this will be the integral from -pi to pi of sine x cosine x dx, we'll let u equal sine x, and so du will equal cosine x. Okay, so this ends up giving me the integral of 1/2 sine squared x, evaluated from negative pi to pi. Just using a u substitution, you can go in and see that's the case. We end up with the integral of negative pi to pi of u du. And so this ends up giving me 1/2, and this will be sine squared negative pi, or sine squared pi, minus sine squared negative pi, and that, in fact, just equals 0. So what we've done, we've gone in and we've evaluated the inner product for each set and found that the inner product for all of them is equal to 0. Okay? Now what do we need to do? We need to go in and we need to normalize the set. So that means we're going to do something like this. Okay? We'll take sine x, okay? And that's going to equal the integral of sine squared x dx, evaluated from negative pi to pi. And if you remember, that's a trig substitution. It'll be negative pi to pi of 1/2 minus 1/2 cosine 2x dx. And when I evaluate that, that's going to equal the integral from, or, well, actually, it's going to equal 1/2 x evaluated from negative pi to pi minus 1/2, and this will be sine 2x times 1/2 evaluated from negative pi to pi. And this will then equal, okay, 1/2 pi minus pi, negative pi minus some negative pi, minus, and then this will be 1/2, and then this is going to be sine of negative 2 pi, or sine of 2 pi, minus 1/2 sine of negative 2 pi. And so what we're left with is just this here. So it's going to be 1/2 2 pi, so this is going to end up being equal to pi. So to kind of clarify that, just to make sure that it's clear, pi plus pi is 2 pi. 1/2 of that is just equal to pi. Sine of 2 pi is 0. Sine of negative 2 pi is 0. So these both zero out, and we end up with pi. That is the norm of sine x. Let's go find the norm of cosine x and the norm of 1. Well, let's start out with the easy one. Let's take the norm of 1. That equals the integral from negative pi to pi of 1 squared, right? dx, which is just x evaluated from negative pi to pi. And so that equals pi minus negative pi, which equals 2 pi. Oop. 2 pi. Okay? And then we'll find the norm of cosine x, and that's going to equal the integral from negative pi to pi of cosine squared x dx. Again, just a reminder from your Calc 2 days, this is going to end up being the integral from negative pi to pi of 1/2 plus 1/2 cosine 2x. And so this will equal 1/2 x evaluated from negative pi to pi plus 1/4, or rather plus 1/4 sine 2x evaluated from negative pi to pi. What we know, this is going to end up zeroing out just like it did in the last time. So what we're left with is this thing here. So this is going to end up equaling 1/2 of pi minus a negative pi, which just equals pi. There we are. So the set, the orthonormal set, is, it'll be, we've got 1 over 2 pi, right? Because that's the vector 1 divided by its norm, which was 2 pi, comma, and then we'll have sine x over pi and cosine x over pi, and that is your orthonormal set. All right? So in this case, we did the same thing that we did before. We just utilized a different norm. Okay? We utilized that function norm where we took the integral on the interval of f of x times g of x. Okay? And then we took the function squared, took the integral of that, and that ended up giving us our norm. So now let's talk about something that's incredibly valuable, incredibly powerful, and it becomes like the bedrock of things like statistics and physics. And this is a thing called the orthonormal basis. So we've got a set of vectors. It's a basis, v1 through vn, meaning that it spans a particular space, that the set of vectors is linearly independent. And what we're going to say is that that basis set is orthogonal if the vectors are pairwise orthogonal, that is that their inner product is equal to 0 for I not equal to j. And it's orthonormal if the norm of each one of the vectors is equal to 1 for every I, for all of them. Okay? So this ends up becoming a really powerful thing. If you kind of think about it, right, if you've got the x-axis, the y-axis, the z-axis, say in 3 dimensions, that's an orthonormal basis, right? You just use those standard basis vectors. All right, we can use what we call E1, E2, and E3. So we've got E1, standard basis, that gives me the x-axis. E2, standard basis vector, gives me the, excuse me, that's E3. E2 gives me the standard basis vectors for y, and E3 gives me the standard basis for vectors for z. And just think about how easy it is to write all of every vector in that standard basis, right? We just multiply each of the vectors by the standard basis vector, and you're done. You've got everything that you possibly need. Okay, because you just, it's just the component of the vector times the standard basis vector gives you a vector in the basis. Well, the same thing's going to happen here too. We know that whatever the scalar is that we're multiplying our basis vector by, that's actually the magnitude. That's the length of that vector. All right, that's incredibly handy. And in addition to that, we can kind of imagine it graphically because everything's actually moving orthogonally. So the orthonormal basis ends up becoming a very powerful thing for us to work with. Now, what we've got here too is we've got another thing that's actually going to end up becoming very important and very handy for us. And so let's say, for example, I've got a set v1 through vk, and that's an orthogonal set of non-zero vectors in an inner product space V. Okay? Then v1 through vk are going to be linearly independent. Now, this kind of makes sense from a theoretical or a conceptual basis, given that the set of vectors is orthogonal, so they've got to all be in different directions because they're all orthogonal to each other. They're all at, perpendicular to one another inside of whatever space you're looking at. So it makes a lot of sense to say, hey, you know what? They're not going to be coplanar, right? Okay, we're just going to, kind of, if you imagine like in multivariable, you took cross products of a bunch of things, or we just imagine that every time I add in another vector, okay, it's going to be orthogonal to all the other vectors, so it can't possibly be on the plane with another vector. It's literally perpendicular. So that kind of makes a lot of sense. What we're going to do is we're actually going to go prove that this set is linearly independent, utilizing some of the facts that we've learned about orthogonality, okay? And then what that's going to do is that's going to allow us to kind of conceptualize these bases for orthogonal vectors. Okay, so what we'll do is we're going to assume, right, we're going to have a set. So let v1 through vk be a set of vectors in V. So we got this set of vectors in V, whatever our vector space is, and we'll let it be also an inner product space. And so we're going to set it up as c1 v1 plus c2 v2 plus ... cn vn is equal to the 0 vector. Okay? And so by definition, if the set is linearly independent, all right, we need to show that C1, C2 through Cn must equal 0. So C1 equal to C2 equal to ... equal to Cn must equal 0. Okay, if they don't equal 0, then we don't actually have a linearly independent set. This is the definition, right? Definition of linear independence. All right, just as a recall. So now what I'm going to do is I'm going to take VI, I'm going to pick a vector, VI, okay? And I'm going to dot it with this vector right here. Now, here's the thing, right? Okay. This vector here, this vector C1v1 plus C2v2 plus ... Cn is actually inside of whatever vector space, okay, is going to be defined by our set v1 through vk, right? And so that's important, right? Okay. So we'll take vi, and we're going to have vi belong to, actually, to make this really clear, v1 to v2 dot vk, okay? So that belongs to that. And we'll take it, we're going to go vi, and we're going to dot it with c1v1, this vector here, plus c2v2 plus ... cnvn, okay? Which we know actually is equal to the 0 vector. And that equals then vi dotted with the 0 vector, right, by assumption. Okay, that's how we set it out. We said it's equal to 0, and so that equals 0. Okay? So, what that means, what we've got to do now is we're going to utilize this information to show that these CIs are all equal to 0. So now what I'm going to do is I'm going to break this up, and I'm going to get then V1 C1V1 plus V1 C2V2. Or actually, this is VI, excuse me, VI with V1 plus ... And you just imagine, without loss of generality, we'll end up with VI, and this will be CI VI. Okay, somewhere in there, we're going to have a vector called the VI vector. Okay, and this is VI. The VI vector, it'll be in there somewhere, and then ... plus eventually VI, and this will be CI, or VI CNVN, right? And that's just because we can distribute. And remember, this is all going to equal 0. So now what I get is I'm going to get, all right, here, this, we'll pull out C1, and this will be then VI, V1. So remember, we can pull out the scalar, plus C2, VI, V2, plus, and then ... CI, VI, VI, plus ... plus CN, VI, VN. And that'll equal 0. A couple things to notice now. Remember that this set of vectors is in fact orthogonal. Okay? So the VI happens to be a vector from the orthogonal set. Okay? And so if I actually take its dot product, remember they're orthogonal, so that equals 0. So what I'm left with is C1, or excuse me, is going to be, this thing here is going to be 0 because I does not equal 1. So 0 plus, and then ... plus CI, okay? And then this is going to end up being VI, all right? And then plus ... 0. So everything zeroes out except for the VIs. And that'll all equal 0, okay? Well, remember that by the, because, right, okay, because VI cannot equal 0 if VI does not equal 0. This means CI must equal 0. So if you look here, VI. Now, if VI happens to be 0, then it's trivial. I mean, like, what's the point? Why'd you put it in the basis, right? Okay, you put the 0 vector in the basis, who cares? I mean, that's not going to make any difference. So we're just going to assume that it's not 0. It's not the 0 vector. So we know that its inner product is not going to equal 0. So what does that mean? Well, that means that CI is going to equal 0 because everything else zeroed out. We were left with just this term, so that means CI has to equal 0. Well, we chose an arbitrary vector ci. If we had chosen c1 or v1, excuse me, we had chosen an arbitrary vector vi. If we had chosen v1, we could have, just as easily shown that c1 had to equal 0, right? This is true for all ci. It was arbitrary. So what we've done is we've shown by definition our ci, c1 through cn, has to equal 0, right, in this set. So v1, v2, all the way up through vk are linearly independent. So we actually just showed that they're linearly independent utilizing those really handy results from inner product spaces. Okay? All right, it's kind of neat. So what we have now is if we know that we have an orthogonal set of vectors, and in fact that we know that they are an orthonormal set of vectors, what we have is we have a linearly independent set of vectors. And if all the vectors are pairwise orthogonal, we get a basis for something. It may not be the entirety of the space, right? Okay, but it's a basis for something. And if I have enough vectors, okay, that are all orthogonal to each other and they're all normal to each other, I find that I can get an orthonormal basis for an entire vector space. And that's incredibly handy. So now what this allows us to do, this piece of machinery is going to allow us to generate orthogonal bases from sets of vectors. And we're going to do that, and that's then going to become something called the Graham-Schmidt process. It's also going to allow us to develop projections of vectors, and you've done some work with projections before, but we're going to do even more work with projections. But let's just start out with this idea. We've got this theorem. We're going to let V be a finite dimensional vector space with an orthogonal basis v1 through vn. Then any vector v belonging to V can be expressed in terms of the basis. So now we're going to express it in terms of the basis. Okay? So our vector v, right, can be expressed in this manner, all right, in terms of that orthogonal basis. And this is how we're going to actually express it in terms of the orthogonal basis. Okay? So remember that a basis is basically, it's like a naming convention for how we name vectors. Okay? So if we have a basis for a vector space, I can actually name any vector inside of that basis utilizing the basis vectors. Okay? And this, in this way, is going to make it really handy for us to be able to express any vector inside of an entire vector space in terms of its orthonormal basis, right? Make it really, really neat, really tidy for a lot of engineering purposes, a lot of statistical purposes, a lot of physics purposes. Okay? So let's take a look at a proof. All right? So we're going to let V be an inner product space. Okay? And we're going to let V1 through Vn be an orthogonal basis for V. All right? So, since it's an orthogonal basis for V, big V, not little v, big V, what we can do is that every vector V will be equal to, and we'll call it C1 V1 plus C2 V2 plus, and then just dot, 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 plus Cn Vn, right? Because you could just take a set of scalars, you could find the scalars in somewhere or another, multiply them by each vector in the basis, and you get the vector in that basis, okay? And it's unique. This is unique for that basis. It'd be really weird if it wasn't. All right? And so what we get then, what we know is that if I take V and I dot it with VI, okay, V, and I dot it with VI, and remember VI is just a member of this orthogonal basis, what I'm going to get is I'm going to get, it's going to be C1 V1 plus C2 V2 plus dot, 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 Cn Vn, all right, dotted with Vi. And so that's going to end up being C1 V1 Vi plus, and then at some point in time we'll have Ci Vi Vi, just like we did before with the linearly independent set, right? Plus dot 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 plus Cn Vi or Cn Vn Okay, and I could just pull out the C's. Did that? Just seen that enough already. C1, Vn, Vi. Okay, and so what we know is that since these are orthogonal vectors, and each Vi in the set is inside of that orthogonal set of vectors, anything that's not the ith vector is going to zero out. Okay, so this is going to essentially be, not essentially, it will be, it'll be Ci, and it'll be Vi dotted with itself. Okay, and that's actually what the value will be if I dot V with an arbitrary vector Vi inside of the basis. And so this is then going to equal Ci, and it'll be the norm of Vi squared. Okay, and that's each Ci is going to be that value. So what does that mean? Well, what does that mean for us? Okay, well, it means that V can be expressed or can be equal to. So what this means is that if I rewrite, I'm going to get that V with Vi. The inner product V with Vi is going to equal Ci, the norm of Vi squared. So to find Ci then is going to equal V with the inner product of V over the norm of Vi squared. And so that's each of the scalars inside of the vector V. So V then, if I just rewrite it, V is going to equal, well, C1 is going to be V1 over the magnitude of V1 squared times V1 plus, and then it'll be V2 inner product over the magnitude of V2 squared times V2 plus, and then you kind of get the idea of what's happening here. It'll be plus, then finally V inner product with Vn over the magnitude of Vn squared times Vn. And so what we've done is we've now re-expressed, okay, we've re-expressed V in terms of our orthonormal basis, or our orthogonal basis, excuse me. So let's take an example to see what this looks like. Let's say, for example, that we have the orthogonal basis. We've got V1 equals -1, 2, and V2 equals 2, 1. All right, we'll just prove that that in fact is orthogonal. We've got -1, 2 dotted with 2, 1 equals -2 plus 2, and that equals 0. So we'll rewrite now, and remember we had to, like before, you got to go in, you got to find the change of basis matrix, blah, 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 right? Which you're like, okay, that's not so bad, but this is going to actually make things a little bit easier. We're going to rewrite, let's rewrite 3, -6, okay? Not 3, -6, that's simple. Let's do 3, 5. Let's do 3, 5 in the new basis, okay? In V1, V2, our basis. So what I'll do is I'm going to take 3, 5 dotted with -1, 2 divided by the magnitude of -1, 2 squared. And then we'll multiply that by -1, 2. And then plus, we're going to take 3, 5 dotted with 2, 1 divided by the magnitude of 2, 1 squared times, in this case, 2, 1. And so what we'll get then, that's going to give me -3 plus 10, that's going to be 7. 7 over, this will be 1 plus 7 over the square root of 5 times -1, 2 plus, and this will be 6 plus 5, that's 11. So it's 11 over the square root of 5, 2, 1. And that, in fact, is our vector 3, 5. Okay? And so we can just utilize this equation right here in order to rewrite a vector in terms of an orthogonal basis. And this is going to end up becoming the foundation for our work in using the Graham-Schmidt process. So this completes the theoretical part of our work with orthogonal bases and orthogonal sets and orthonormal sets. We're going to be then using this information in order to develop the idea of a projection. And you've probably seen projections before inside of multivariable calculus. I'm just going to iterate those more inside of another video about orthogonal projections. We're going to use that information in order to kind of develop the Graham-Schmidt process. But for right now, this kind of lays down some of the fundamentals that we need in order to kind of think about orthogonal sets and orthonormal sets. All right, and hopefully it allows us to think through things that are maybe not as common, right? Like utilizing those function inner products, maybe even be able to think through some of the complex number of inner products too. All right, so what we've gone through today and gone through inside of this video, we've gone through the defining of orthogonal sets, showing that we have orthogonal basis, what it means to normalize something, to prove that a set is orthogonal, okay, and then also to generate a vector inside of an orthogonal basis.